It's my pleasure to welcome Eleanor Rieffel here from NASA Ames up in the Bay Area. She's very kind to accept our invitation to come out. Notably, Eleanor is the author of this textbook here, which I use to teach my first class here on quantum computation and quantum information. And I see some of my students from that class in the room. It's sort of a treat you can meet the author. And all those long hours of staring at this textbook, you can assign blame. But to give you an idea of who Eleanor is, I'll read her bio, which is a fantastic bio. Eleanor joined the NASA Advanced Supercomputing NAS division at the NASA Ames Research Center in 2012 to work on their expanding quantum computing effort after working at FX Palo Alto Laboratory Incorporated, where she performed research in diverse fields, including quantum computation, applied cryptography, image-based geometric reconstruction of 3D scenes, bioinformatics, video surveillance, and automated control code generation for molecular or modular robotics, which is a mouthful. It's done a lot. Her research interests include quantum heuristics, evaluation and utilization of near-term quantum hardware, fundamental resources for quantum computation, quantum error suppression, and applications for quantum computing. She received her PhD in mathematics from UCLA and is best known for this textbook right here. So she's fantastic in her field. She's very well respected, and we are very delighted to have you here. So I look forward to what you have to say.
Thank you so much, Justin. It's a real pleasure to be here. This is going to be a little bit of a miscellaneous talk. So I'll give some high-level overview and then get a little bit more technical. And I hope that the students here will correct me when I go wrong. So, because I'm pulling some of that material out of the textbook, so be on your toes. So I'm here, as Justin said, from NASA Ames. We actually have a fairly large quantum computing group at this point. There are 11 of us, 2 very part-time people, but 9 people working full-time on quantum computing related work. And I'll touch a little bit on what we're doing there, but mostly this will be an introduction to the field. Feel free, I'll be around this afternoon. Feel free to come and ask me more about our research later in the afternoon. And also tell me what you're doing. So the first question I often get is, why in the world is NASA interested in quantum computing? So I thought I'd just head that off right at first. So NASA is just constantly confronting really challenging computational problems, and that inhibits them from being able to do some of the missions they want to do. And many people, especially young people, think of NASA as astronauts, but there are way more people working on simulations and algorithms and computational efforts. And I strongly recommend that you go see the movie Hidden Figures if you haven't already. So we have one of the biggest supercomputers in the world. And right before I started at NASA, NASA did this crazy thing of trying to land the Mars rover Curiosity. And that included the, quote, 7 minutes of terror, which really didn't look like it was going to work. But because people had done a lot of computational and physics modeling, it actually successfully landed the rover, which has been sending us all sorts of great data. So what the quantum computing team there, our mandate is to determine the potential of quantum computing to enable more ambitious NASA missions in the future, in particular to enhance our quantum computational abilities in the directions that can help with some of the computational challenges that NASA faces. And we're at the very early stages in quantum computing, and so this is a quite uncharted territory, but very, very exciting place to be. What makes it particularly exciting is that not at NASA Ames, where we're a theory group, but we work very closely with experimental groups and companies putting together quantum hardware. So there's emerging hardware coming out in the next decade. Just will be really, really exciting as different groups come out. So I've listed some of the groups that are aiming for large number of qubits, The 4 groups on the right are doing universal quantum computers and are aiming for 40 to 100 qubits within the next year or two. And there are also special purpose quantum computers like the D-Wave quantum annealer that we've been working with for a while that runs one type of quantum algorithm, and we can explore with that. And so one of the things we look at is, okay, what can we do with this exciting but early technology? It's very limited. It really is too small to solve any of the huge computational challenges that NASA and others face, but we can get a real sense from playing with it as to what it might be able to do in the future and what aspects of quantum computing might be able to help with algorithms going forward. And so that's our focus. And one thing I want to emphasize right away is that there are some really exciting quantum algorithms that are known, like Shor's algorithm for factoring, that we'll touch on later in the talk. And there's a provable quantum advantage there, subject to very common conjectures in computer science. But there's only, depending on how you count, a few dozen such things for certain problems. There are also a handful of limitations on quantum computing that are known. But for almost everything, including most practical problems, it's just not known as to whether there's how much quantum computing can help out and what sort of algorithms will help out. And this is not surprising. So in classical computer science, most of the things that are run, for example, on this supercomputer at NASA, there's not a mathematical proof that says this algorithm that we're running is the best possible, or even that this algorithm that we're running this year is better than the one that's run last year. What happens is that people run it empirically and see how it does on test cases and use that to guide how to generate better software. And that's why there are many competitions in satisfiability problems, in planning and scheduling, in machine learning, etc. And so far, that hasn't been an area that we've been able to attack with full-scale quantum computing because there's an exponential slowdown, as we'll see, in the general case to simulate these algorithms, and we didn't have the hardware. And what the next decade will allow us to do is play with quantum hardware that gets beyond where classical simulations can take us, and will be very exciting in terms of being able to figure out what is useful for these algorithms, what hardware gives us the most buy, and will give us a lot of guidance going forward as to what the potential is here, what problems to attack, and that's what NASA is really concerned with. So I said a lot of this already. We really want to determine the breadth of quantum computing applications going forward and taking advantage of the emerging quantum computing hardware. And we're doing everything from trying to figure out how to harness very basic quantum effects for algorithmic purposes and understanding, modeling some of the quantum hardware up to high-level algorithm design, quantum program compilation methods, and the like. And our initial target was quantum annealing, which I'll tell you some more about. And that was because the earliest quantum hardware that was available was this D-Wave quantum annealer. And it was interesting to see what can it do, what can't it do, how quantum is it, what can we see there. And now we're expanding that effort beyond quantum computing to also look at other near-term devices like the ones I showed on the previous slide. And designing and vetting quantum heuristics is a really tricky process because you can't just blindly do this. You need to develop intuitions, but heuristics by definitions are things that you may not be able to have a mathematical proof that it's doing better than before. So you have to figure out how are you going to make reasonable tests to figure out what is looking promising here. And there are a bunch of quantum properties, I've only listed some of them as sort of flavor, that you could potentially make use of here, but the tie between these special quantum effects and making use of them in algorithms, in many cases, is not so clear yet, and is a very exciting area of research. So as I said, we're going from very low-level physics insights all the way through trying to project what the applications will be. And we've looked particularly at planning and scheduling, fault diagnosis, and machine learning to try to develop intuitions for quantum heuristics there. And we're slowly expanding on those areas, expanding on the algorithms we're looking at, and trying to understand what this indicates for future architecture design. So we're in constant contact with the people who are building the hardware. How you want to do the programming and parameter setting for these algorithms. And also a really interesting area is hybrid quantum classical algorithms, because we don't expect, at least for decades, that quantum computers will take over from classical computers. We expect that they will complement them. And so that we want to be able to use quantum computers as a very fast coprocessor for the things they're good at, while keeping a lot of things on the classical side. And there's some very interesting work as to how best to do that. And we're looking both at application-specific solvers and more general solvers. So that's sort of my high-level approach, and then I want to go back and tell you more technically what quantum computing is, and give you a feel for why there's something really special here. So for some of you, like those who've been in Justin's course, this will be, the first part of this will be largely review, but I hope it will nonetheless be helpful. And I'm not going to ask for questions on the overview part yet. You can ask me at the end. But as I go into the more technical part, please ask, especially if there are questions about that could clarify what I'm saying, because it's a very diverse audience, and I don't know what's familiar and what isn't. So please feel free to interrupt me at any point. So quantum computing really got started with a recognition by prominent people like Feynman and Manin that certain quantum mechanical effects are not efficiently simulable on a classical computer. And that's interesting in and of itself. But then you can turn the problem around and say, okay, we have these things that quantum mechanics can do very quickly, and you can't simulate them on a typical computer. Can we now make use of those effects to do more than just those simulations, fast simulations of the quantum effects? And it took a while for people to figure out what that might even mean. And really, a lot of the work was getting our heads around something that had started to be less intuitive classically. So one of the really amazing things in computer science as we know it is that most of us work on our computer just fine without knowing at all how it works. We may know how it works because that's interesting, but we don't actually have to know about it when we're programming. And so this abstract model of computation is really successful, and it's easy to forget that what's going on is actually a physical process. And that physical process is very grounded in classical physics. So for those of you who have taken a really theoretical computer science course, if you think about what a Turing machine is, it's a very physical model of a machine with a tape and what's getting put on the tape. And of course, our everyday computers are very physical devices. So what if you took this standard model of computation, and instead of grounding it in classical physics, you grounded it in quantum physics? What would that mean? Since quantum physics is actually the physics of our universe, up to some corrections that might be needed for general relativity, this is what is possible for us to do in this universe. And so we really need to figure out, if we base computation on the actual physics of our universe, what can we do with that? So the earliest quantum algorithms were not what you would probably think. And I do this to try to emphasize that people's intuitions here are not necessarily very good. So the first algorithms that people came up with solved efficiently with certainty problems that could only be solved efficiently classically with high probability. And the first bit of information that most people take away from quantum mechanics is that it's probabilistic. And yet the first application here was doing something with certainty that couldn't be done efficiently with certainty classically. And that was a provable difference between the two, but was not for a particularly useful problem. But some of those early algorithms led Shor to realize that perhaps he could make use of some of that structure to find a polynomial time quantum algorithm for factoring in the discrete log problem. And this is really major because those are the problems that underlie all public key encryption that's used today. Every single one of those algorithms. So RSA, El-Gamal, elliptic curve cryptography in general, those are all broken by quantum computers. Fortunately, at the moment, there aren't quantum computers that are large enough to solve these problems of interest. But this is a big push for both finding out what quantum computers can do and building the hardware, and also pushing on the classical cryptographers to try to come up with something that's robust against that. So there's an exciting race there. Will the classical cryptographers be able to figure out something that's really solid against quantum computers before the quantum computing community builds large quantum computers? So exciting there. That all, Shor's algorithm was very exciting, but the initial reaction to it was, well, yeah, but quantum mechanics is really fragile. So, while in theory this would work on a perfect device, it will fall apart if you actually do it on anything practical, because there's got to be errors, and there's no way to do standard error correction. As we'll see shortly, you cannot clone an unknown quantum state. And classical error correction makes use of copying all the time. So how do you do this? And so a really big advance here, in my opinion, just as strong as the Shor result, was figuring out how to do quantum error correction. And those two results really sent the field off into being, instead of just a minor subfield for people who were interested in these odd sorts of quantum mechanical effects, into center stage. Around the same time, there was Grover's unstructured search algorithm, which outperforms any possible classical algorithm for the problem of unstructured search, which is not the most practical of search problems, but again, it's provably different here. One disappointment was that between that result and about 2002, there really wasn't very much in the way of new algorithms discovered. And that's because it's really, really hard to figure out how to make use of these effects and what's going on in this algorithm development. But in 2002, there were a number of breakthroughs that were very exciting, and that's what's led to the dozens of algorithms that I mentioned before, and also some heuristic algorithms that we'll be exploring. So you may say, well, she hasn't even told us what a quantum computer is yet. And yeah, that's a problem. And I'm not even going to be really helpful, because the first thing I'm going to tell you is what it isn't. Just because a computer uses quantum effects does not mean it's a quantum computer. So the processors we use these days use quantum effects for a variety of things. But they haven't changed what you mean by the fundamental unit of computation, and they haven't changed how you manipulate the computation in that abstract model. And so when the quantum effects were introduced, there wasn't a change at the programming level as to what you did. So most of us could just sit here agnostically and program the way we used to, and it was completely transparent to that. quantum computing changes the very basic notions of what we mean by information and manipulating information. So you go from bits to qubits, and we'll talk about what those are in a little bit. We go from logic gates to quantum logic gates, and from algorithms to quantum algorithms. And I want to emphasize that the terminology here differs from such terms as DNA computing, where DNA computing is talking about the substrate you're computing on, whereas here we're talking about a fundamental difference in what we're thinking in the abstract model of what information is and how you manipulate it. So I'm now going to try to give you a very quick overview of some of the more so this is going to get more technical at this point and give you a sense for quantum bits and some of these things. And I'm going to run out of time because it always takes me, I always put more in talks than we really can do. So don't worry about the slide count down here. We'll take whatever time, we'll get as far as we need in this, and I'll do a real quick sum up. And again, please feel free to ask questions. So I like to start, since this is physics, and the fundamentals is physics, I like to start with an experiment. And sometimes I actually bring along the polarization filters here to show it, but I'm just going to do it in slides. I apologize. But I urge you to go and do this yourself. So you can do it with polarization filters you can get at a camera store if those still exist. Or you can do it with sunglasses, though it's a little trickier because they're sort of an odd shape and harder to hold.
And I have these in my office. For students who know me, I will show you later.
Excellent. So we have a beam of light. You can take a laser pointer and you can stick this polarization filter in front of it, and it's polarized in the horizontal direction. Then I take one and I put another polarization filter in, and it's polarized in the vertical direction. And because they're at 90 degrees with each other, no light gets through. Okay. So now the trick question for you is, what if I stick a polarization filter in right in between those at 45 degrees? Okay. So I'll tell you the obvious answer, which is wrong. The obvious answer is no light gets through these two filters. So if you add another filter, well, clearly that only makes it even harder for light to get through, right? What could possibly be wrong with that argument? Okay. So, strangely, it actually increases the amount of light getting through. Now, there's a perfectly good classical explanation of this in terms of light as a wave, but what if you look at this in terms of individual photons? What are those individual photons doing that could explain this? And the reason I'm going through this is this will give us a good sense for what a qubit is. So, the polarization of a photon can be represented as a two-dimensional vector of unit length. That's a complicated way of saying that you can choose a direction. And for those of you who care, this can also be a complex number. For those of you who don't care, that won't be important for this talk. It is important for quantum computation. So we can take horizontal and vertical polarizations as our computational basis, where we're thinking as this is my 0 and this is my 1 for a standard computing bit. And then a polarization can be expressed as a superposition of those. This is just basic vector calculus, where I can express this vector as a sum of this horizontal piece and this vertical piece. And then, and by the way, the notation here is just a fancy quantum mechanical notation that helps us do some of the calculations. But basically, we're putting these things in Dirac's notation for vectors. These are called kets. That just means that I have a vector that's pointing up. I have a vector pointing to the side. Later, I'll have other things in there which are just labels for these vectors. Okay. So what happens with these polarization filters? Well, they're basically quantum measuring devices when you're looking at the single photon level. So quantum measurement device, for whatever reason in this universe, what a quantum measurement device does is it chooses an orthogonal subspace decomposition. So two things at 90-degree angle in the case where we're just dealing with a single photon. And you can choose any set of those, but that's going to be your polarization filter. And then for a horizontal polarization filter, it measures either horizontal or vertical. If the photon is in the horizontal direction, it gets through the polarization filter. If it's in the vertical direction, it doesn't. But what happens with photons that are polarized at something in between? That's really interesting. What happens is that it's absorbed with some probability, whatever corresponds to the component in the direction of vertical, and it's let through with some probability corresponding to the component of the vector in the direction of horizontal. And once it is passed through the filter, it takes on that value. So it's no longer in the polarization that it had been in. Now it's horizontally polarized in this case. And polarization filters at other angles work in similar ways. So let's quickly go through this experiment and see what happens. Okay, so we have our horizontal polarization filter, and remember, any light that gets through there is polarized horizontally. Excellent. And now it hits a vertical polarization filter, and what happens? It's all blocked. Why? Because, yeah, it's orthogonal. This vertical piece has no component whatsoever in the horizontal piece has no component whatsoever in the vertical direction. Okay, now we add this polarization filter at 45 degrees. What happens? Well, now our horizontal piece has a component in the 45-degree direction. In fact, the 45-degree direction is half horizontal and half vertical, and so half of the light is going to get through here. And then when we hit the vertical one, it again has half in that direction, and so we do get some light coming through, and that's the explanation for that at the photon level. So let's go forward now and say, okay, what's a quantum bit? So think polarization states of a photon. So it's a two-dimensional quantum system of some sort, like a photon. And we choose two states that we'll consider corresponding to our classical bit values. And then our possible values for a qubit are these superpositions, possibly complex, of those two values. And this is a big difference between classical bits and quantum bits, is that they can be in these superposition states. Okay? And that in and of itself is very interesting. It can enable you to do things like quantum key distribution, which unfortunately I don't have time to talk about. But what really is exciting is to go to multiple qubits. But before I do that, I just want to emphasize a couple things about these quantum superpositions. So I've written two quantum superpositions at the top. They're both 0 and 1, but one of them has a -i before the 1. But they both have, if you take a look at these in terms of, they're both sort of half 0 and half 1. So what I want to emphasize is that these are different states and will act differently in different situations. So it doesn't mean that these act like they are half 0 or half 1, or that they're 0 or 1 with some probability. These really are distinct states. And if you think of the polarization example, you can sort of get an intuitive feel for that. If you have something polarized at 45 degrees, it really doesn't intuitively make a lot of sense to think of that as, well, it's either 50% vertical or 50% horizontal. And that intuition is actually correct here. So the superposition is a state that, when measured in certain bases, so for example, the 45-degree angle polarization thing will always get through a 45-degree filter. Okay? But when in other cases, the results will be probabilistic. And the difference between the +1 and the -I is a difference in relative phase, which turns out to be quite important here. The result of this is that it's philosophically tricky to say what a quantum superposition means. And one of the things that's philosophically tricky here is that some people will say that it's not tricky at all. But two of those people may not agree on why that's not tricky, but we won't go there. Okay. The nice thing is that it's mathematically straightforward. And there's a quote, and Justin nicely left the book here so that I can read it exactly. There's a quote by Murray Gell-Mann that says, "Quantum mechanics, that mysterious, confusing discipline, which none of us really understands, but which we know how to use. And the reason we know how to use it is because it's mathematically straightforward. And if we just stick in the language of mathematics, I'm a mathematician by training, so I have to do ads for this, then we're all okay. So the language of mathematics is why we're okay with quantum mechanics. Okay, I can stop the talk now. I've gotten to the main point, but maybe you'd like to hear a little more. So measurement of single qubits is just like for the polarization filter. It depends on these amplitudes in front of the zeros and ones, and it returns the value 0 with a certain probability and 1 with another probability and projects the state to one corresponding to the measurement result. And a qubit can be measured in any of these different cases, but only one classical bit can be extracted because you have to choose a measurement basis, and once you've measured, that's going to give you out a bit, and it changes the state, so you can't do another measurement on that state. Okay, and a related thing is that you can't copy unknown quantum states, because if you could, then you could route around this by making a bunch of copies and then measuring them sequentially. And there's actually a very simple, very basic linear algebra proof for this fact, but it's a lot of, it's very important for like the security of quantum key distribution and many other things. And so it's both a minus and a plus for quantum applications. And that's one of the art of quantum information processing. It's trying to figure out how to take these odd properties of quantum mechanics, many of which people just thought were problems for a long time, and make use of them algorithmically. So as I mentioned, what we really want to see, and this is going to get more technical, so I just want to give you a feel for it. What really is exciting here is when you start to combine qubits together. And again, the mathematics here can really help you get a sense for why there's a real difference. So if you have a vector space with a bunch of basis states, so you can think of this as a set of photons, if you like, and each one of those has, so just think of two photons, for example, one with vertical and horizontal polarization and the other with vertical and horizontal polarization. If you thought about what happens when you classically combine these, you just do a Cartesian product where you have these basis states and you consider them as separate entities. But that's not actually how quantum state spaces combine. They combine by something called the tensor product, and there the dimension increases. Instead of adding these bases together, you combine the bases in this tensor product way, and you get a much larger state space because you're multiplying the dimensions there. I would love to tell you more about it, but for some reason, I don't know why, Justin only gave me an hour. So I just want you to get a feel from here that these things combine in a very different way, and the state space is much larger. And what are those states going to be? There's a much larger state space, but how do we think of those? And what's really important here is that you can't think of all of these states as this qubit is in this state and this qubit is in this state. Some states, quote, product states, can be done that way, but other states are, quote, quantum entangled. And you can't separately describe the state of this photon and this photon. And that's one of the initially unintuitive properties of quantum mechanics. But guess what comes to your aid here? You can describe this all very, very formally, mathematically, and do the calculations and see what happens. So here, we can just think of these as our two photons, with 0 corresponding to vertical and 1 corresponding to horizontal. And we have our basis, which is these 4 states that are just product states. So both photons are vertical, one photon's vertical, the other's horizontal, etc. We often write these in a more compact form where we don't have to write the tensor product. And then because these are binary values, we can even make it more compact and write it where in binary notation 101 is actually 5. So I'll be using that somewhat interchangeably. And that's one of the places where you might just ask some clarifying questions, because I'm going through this very fast. So if this doesn't make sense when we do some of the examples, stop me and I can go through it. So we can write all of our quantum states in terms of amplitudes in front of each of these basis vectors. Okay? So if you have all 2 to the n states here, then I get 2 to the n amplitudes here, and I'm just going to call I, that's in my binary, that's going from my binary notation to however I want to represent those integers. Now, since 2n, which is what you'd get if you classically combine these, is much less than 2 to the n, most states can't be written as a product. Okay? And these entangled states, the ones that can't be written as a product, really have no classical counterpart. And there are a lot of unusual effects that people here can tell you about Bell states and other entangled states that are very interesting. But I'm not going to sidetrack to that because we want to look at quantum computing particularly. So you can get these states, and then what happens when you measure a multi-qubit state? So say I measure the second qubit of this state. So it's a linear combination of these basis states, and for some of them, it's in the qubits in the 0 state, and some of them it's in the 1 qubit state. And a similar thing happens to what happens in the single photon case, which is that basically you look at what's the amplitude in front of the ones with a 1. So in this case, you have A3 and A7, and you take that amplitude in front and square it. I think I didn't say this in the polarization example, but it should have been fairly clear from Pythagorean theorem that you were squaring those amplitudes. So you square A3 and you square A7, add them together. That's the probability that you get a 1. And you can compute A0, A1, and A5. The squares of each of those, sum them up. And since this is a unit vector, those will add to 1. So that really is a probability. And furthermore, what do you get as the state out? Because you remember, if you measured, you projected to that particular state. So if you measured and got horizontal, it became horizontal. Well, now we're just measuring 1 qubit. Well, what we end up getting is just the components that, so if it measures as 1, we get just the components that have 1 in there, and you have to normalize to make it a unit vector. And similarly, if we'd gotten 0, we again normalize and make it a unit vector where we've just taken the 3 terms where it's 0. So it's very similar to what's going on in the photon polarization case. Here's just an example of that entangled states really exist. So if I try to write this EPR pair in terms of a product of a single qubit state with another single qubit state, here's how they combine. But say that again?
EPR means what?
Einstein, Podolsky, Rosen. And these are, this is the most famous first paper talking about entanglement. And just for historical reasons, they didn't actually talk about these pairs, but they got named after that. So we want to get out of this the state with 0, 0, and 1, 1 represented, but without 0, 1, and 1, 0 represented. Well, the only way you can do that is to have both of those 0, but then that implies that either A0 or B1 is 0, and either B0 or A1 is 0, and you just can't get, that would mean that either this or this is 0, so you can't get the state out. And so there really are entangled states, and let's try to figure out how to use these. So a lot of what's going on in quantum computation is how to use entangled states or other properties that are non-classical to do computation. Now I'm going to sort of speed up and give you a high-level view of quantum computing, because I haven't talked about any algorithms. I've just talked about sort of the pieces there. So there are 3 views of quantum computation. There's a quantum circuit model that's the easiest to grasp when you're coming from a computer science perspective. There's also adiabatic quantum computing and measurement-based quantum computing, which if I have time, which I won't, I will touch on. But you can ask in questions if you're really curious. In the circuit model of computation, and note, I'm finally telling you what a quantum computer is, sort of. So you have a n-qubit register. You can think of these, if you like, as n photons. And then you can make quantum operations on this register. So and it turns out that just operations on 1 or 2 qubits suffices. You don't have to do it that way, but it can get you any quantum computation. So you can have a sequence of these 1 or 2 qubit gates acting on the qubits. And then you may measure some or all of the qubits in the register. And note that the control here is classical. You're telling, you can write a program, we write programs in Python, for example, to tell us what to do on quantum computers. But then the actual steps, these gates, are carried out on the quantum hardware. And then you need to interpret the results of your measurements to get information out. There are single qubit gates, just like there are logic gates in classical computation. Some of them are similar to ones you've seen, like negation. But there are other things that allow you to change the phase, for example. If you remember the +1 versus the -i that we saw early on, you can do changes of that sort. And you can change bases, so you're going from 0 to 45 degrees, and so 0 to 45, and 1 to 45 over here. And so there are lots of single qubit gates you can do. And you can also do multi-qubit gates. I've just written down one that's easy to understand classically, which is a controlled NOT. So if the first qubit is a 1, then it switches the value of the second qubit in the standard basis. One really interesting thing is to see what happens with this gate if you do it in other bases, other than the computational basis. So if you're looking at things at a 45-degree angle, what happens here? All quantum gates are linear, and quantum computations are reversible, and quantum gates do not dissipate energy. All of this falls apart once you have noise, but in the ideal case, you can model it this way. And when we model noise, we model this often as these transformations, but including interactions with an outside environment or bath that we don't know very much about and perhaps can't measure.
Are these gates theoretical, or are there people how to build these things?
So these gates are, so what I'm writing here is just the mathematics. but the hardware I presented at first, people do know how to build these gates, or they may be using a different model of computation, like adiabatic quantum computation. So, but yes, people have control knot gates built. People have universal quantum computation on a small number of qubits, and they're going to be able to do these on 40 to 100 within the next year or two. Now, I mentioned there are infinitely many single qubit gates. You can just take a small subset of that and be able to approximate everything closely. And so people generally just take a small subset of these single qubit gates when they're implementing them. But in theory, you could do all of those. One trick you can do here is to compute in quantum parallel. So you start with a superposition of all possible input states, and then you compute a classical, the quantum analog of a classical function on that, and you get a superposition of all possible input states with all the values on those input states. If you just measure right away, this doesn't do you any good, because all you do is you get a random value out of a random input and a random output, and you can do that perfectly well classically. So the trick is to figure out, okay, how can we make use of this complicated superposition and actually get something we care about out? And that's what people really struggled with for a while. And one thing you can do is you can do a quantum Fourier transform on this. And what you end up with is having information about the frequency encoded in your states instead of about the, so if you, for example, you had a periodic function as f, then you're going to get a very simple periodic function when you take the Fourier transform, where it has a spike at the frequency and not at other places. And this is the heart of Shor's algorithm. So this might be a little bit ambitious, but here's Shor's algorithm in one slide. Okay. So first you use elementary number theory to represent the factoring of a number in terms of finding the period of a certain function. This was known way before quantum computing and is standard in factoring attempts. Then you compute f simultaneously using quantum parallelism. Then you apply a quantum Fourier transform, so you get only multiples of the inverse of the period. Then you measure. You take the denominator of your guess as the period, and with some probability you get something that's a factor. You can check this easily. If it succeeds, okay, you've found a factor. If it doesn't succeed, you try again, and you can do an analysis and see that it succeeds with high probability. So now you know you have a perfect understanding of the most famous algorithm in quantum computing. In one slide. And now I'm going to skip some things because I have 1 minute left. Quantum error correction is very important and really fascinating. And in certain ways, it's the most mature area of quantum computing at this point, after people initially thought it was impossible. So and it's beautiful. And there are fault tolerance theorems. So even if you have an imprecise implementation, you can figure out how to make a more precise implementation that's robust to that. And there are threshold theorems that if the error rate is below a certain thing, then you can indefinitely do computation like we do classically. So that's really, really exciting. And one of the goals is to push things, push those threshold theorems down, push our experiments up so that we're within that range. In other areas like adiabatic quantum computing or quantum annealing, it's not known whether there's threshold theorems. So there's pluses and minuses of those different ways of doing quantum computation. I mentioned quantum heuristics before. That's a big interest of ours. And quantum annealing is one type of meta-heuristic for this. And I can tell you more about this afterwards. One thing I wanted to mention is that I fully believe that quantum computers will be built. But even if they somehow are never built, there's already been a big win here, because there are a number of classical algorithms that were inspired by quantum computing, and the number keeps growing. And so there was a 2009 survey, and there have been many, many more such since then. So many people in computer science feel that if you're going to be on the algorithmic design or analysis end of things, you have to know quantum computing, even though quantum computers, except really small ones, haven't been built yet. Takeaway points. One of the things I hope you walk away with is that what we can compute really depends on what the physics is of the situation. And so changing our underlying model of computation from a classical physics model to a quantum physics model changes what we can do computationally. There are also many open questions. One of the ones we're most fascinated by is, how broad will the impact be of quantum computation? And how will that happen? What are the algorithms that we're missing so far? And we're particularly interested in heuristic algorithms where we can play with the hardware and see what happens. It seems really unlikely to me that the only cases where quantum computing provides an advantage is where we can prove mathematically that it does. In classical computer science, most of the time you can't prove that. So why would that be true in the quantum case? There's much to be understood about the source of the power of quantum information processing, what different aspects of quantum information actually give you the quantum advantages we see, and also how can they be harnessed for future algorithms. I really believe that there's an exciting decade ahead as we explore all of these things, and way beyond this decade as well. And I will end there. Thank you very much.
Eleanor, for a very clear and very technically accurate presentation. I hope everybody understood 100%. But in case people didn't understand quite 100%, they were at the 99% level. Are there any questions?
Asking a question doesn't necessarily mean you didn't understand something. Great.
How close do you think we are for quantum computing disrupts public key encryption?
I think so it depends a little bit what one means by disrupt. So I think we're already at the point where it disrupts in the following sense. So NIST has already suggested that people expand their key size to prepare for whatever public key encryption will be determined to be quantum secure going forward. So it's already having an impact in that sense. On the other hand, while NIST made that recommendation, they didn't say what the replacement would be. So another way quantum computing is having an effect is that it's pushing the the classical cryptographers to think really, really hard about the, quote, post-quantum era. So what public key encryption system are we going to use once there are larger computers? And we better start thinking about this now, because it is not easy to come up with cryptographic algorithms that withstand the attacks of brilliant people as they try to figure out how to break them, and brilliant algorithms. So that's a very active area of research. On the other hand, if you're asking, okay, I have this data that I really don't want people to ever find out, and I have used RSA encryption, when are people going to find out? I think it's going to be a ways. So it's really, really hard to predict. I would be astonished if it came within 5 years. If it came within 10 or 15, that would be very, very exciting. My own guess is that it will be a little bit longer than that, but it's possible also that people will figure out how to do very, very special purpose targeted processors at those particular applications, for example. So it's really, really hard to say. But that's my best hunch.
From an engineering perspective, how will people actually use quantum computers? And what I mean is, how do you debug the quantum computing algorithm? Is it through proof of correctness? And if so, what does that mean for heuristic algorithms?
Yeah, so I'll take the last part of your question first. So for heuristic algorithms, you can use standard techniques for those algorithms, just like for any other algorithms, to make sure they are doing what you intended for them to do. You may not be able to prove that they outperform some other algorithm, but you can check using the same exact techniques that they are doing what you intended. Now, debugging is really, really tricky, depending on what you want to do with your debugging. So one of the tricks there is that, as you saw, measurement affects the quantum state. But one of the areas of one of the great things about error correction that I didn't manage to talk about is that you can make measurements, if you set things up right, to determine that an error has occurred. So, for example, that a bit has flipped without determining what the value of that bit was. So if you can determine that a certain quantum transformation happened to your system, but you don't know anything about what state it was in, you can then undo that transformation and get back to where you were, even though you didn't know where you were. You just know what happened. And that's very, very powerful. And so it's in the gate model area, that's very, very mature. So debugging there is, it's still tricky, but it's people sort of know how to do it. In quantum annealing and adiabatic quantum computing, which is more of a continuous analog process, people don't know how to do it so well. They know how to stabilize things somewhat, but there's some very tricky problems there. Other questions?
The name of your lab is Quail?
Yes.
Artificial intelligence?
Yep.
Can you just give us like a one-slide version of what is quantum artificial intelligence?
Yeah, so early on I mentioned that some of the areas we're looking at is in fault diagnosis and in planning and scheduling and in machine learning. And basically, these are areas where people in the artificial intelligence community have been looking at very, very hard problems in that come up in industry, come up at NASA. And the aim is to gear our application work towards those problems. And so it's artificial intelligence more in the sense of quite grounded applications rather than trying to create something that appears to respond to you as a human being, though conceivably these applications could take you in that direction as well. So I hope that, okay.
You're really dealing with the standard machine learning, deep learning, well, machine learning type of AI issues, and you're just trying to solve those problems using quantum technology.
Right. So yeah.
It's not a new take on artificial intelligence.
It's
applying quantum techniques.
Yeah. So the artificial intelligence part is the problems are classical for the most part. There are a few exceptions there, but but we may take very different tacks. So, for example, in deep learning, one of the tricky things, one of the computational bottlenecks there is to be able to sample efficiently from a Boltzmann distribution. And one possibility, and there's not proof here, but people are exploring this. So one possibility is that you could be able to sample from a Boltzmann distribution more efficiently using quantum computing techniques. There are other cases where we know it is more efficient to sample using a quantum computer than a classical computer for certain distributions. And the question is, how broad is that, and does that set of probability distributions intersect those that are of practical use? I think I saw somebody, yeah.
Since you don't any longer have just binary states, is some non-classical logic brought to bear on how you might analyze some of these?
Yes, so that's an active area of research as well. And it's something I know on the really formal logic side, it's something I know less well, but there was an older field of quantum logic that some of which bears on this, some of which doesn't apply that much to this, but they're very interesting connections there. I'm guessing that some of the other people here might know more about that than I do, but
Quantum logic.
yeah.
Yeah, we have some math faculty who happen to love quantum logic.
Excellent. Yeah.
Other question? I have a long question for you. Currently, just to bring people in the room who don't know up to speed, IBM has a 5-qubit processor that's working and in the cloud. So people can actually log on and run quantum algorithms on 5 qubits already. They just announced a 17-qubit processor. Google has a 9-qubit processor with plans to have 49 by the end of the year. At what scale of this working quantum hardware does it become really interesting for you?
Yeah. So first, let me also mention that if you want to use the D-Wave quantum computer, we have time that's available to people at universities and elsewhere. So if there's a process through one of our contracting organizations, so I can give Justin that information. So I probably should have mentioned that earlier. So I think there are different levels of interest. Like we're very interested in talking with people who are even doing very small qubit experiments to try to understand things like debugging or characterization or the like. But from an algorithmic point, where does it really get interesting? Well, around 40 to 50 qubits, even with our huge supercomputer, you can't simulate that in any reasonable amount of time. And it depends a little bit on the algorithm. For some algorithms, you can push that to another 10, 20 qubits, et cetera. But in the general case, you can't get past that. The other thing is a lot of us want to just work on our laptop and get results back in a few seconds. And one way we can do that with some of this hardware is, even if it would be classically simulatable, if we use something that's more than 20 qubits, then you can probably get the answer back quicker from the quantum hardware than you can from from a classical simulation that you're running. So you're already getting a win there. And it's a little bit hard to tell on the quantum heuristics how many qubits you need, but my feeling is that once you're beyond what we can simulate classically, you can already start to get some further intuitions into these quantum heuristic algorithms, and that by 100 we're very happy, and by 1,000 we're thrilled, and by 10,000, but these probably have to be fault tolerant or close. You can actually do some things of practical interest. So.
I guess at this point we can take the discussion offline. If you have more questions, feel free to come up. And let's thank our speaker again.